and welcome to Chapter 2, Section 9. So we've talked about a ton of things in this chapter. Now we're on the final section. We've covered a lot of material, and we're just going to finish out this chapter talking about what we're going to call weighted averages. So we've translated sentences into equations in the past. Now we're going to solve some problems with averages. So we'll solve some mixture problems. We'll solve some motion problems, and it's going to be a lot of words. But we'll just write those down, copy the tables that we see, and we'll talk about it as we get to it. So our first example, there are a lot of words there to digest. You don't have to copy down this paragraph, but we are going to write the table that comes after it. So as we're looking at this and breaking it down, it's important to pay attention to the words that we see and the numbers that we see. So I'm going to circle what's important here. So we've got all these things going on. So someone's feeding their cat gourmet food. It costs $1.75. She also is going to combine it. So she's mixing in gourmet food with cheap food that's only 50 cents. The question is, how many pounds of cheaper food should she buy to go with 5 pounds of gourmet food if she wants the average price once she mixes it to be $1 per pound? So there's an equation there hidden in all of that. So first, this is the table we're going to need to copy down for this problem. So let's break down what's happening in this table as you're copying that down. So on the left, we see three things. First, the gourmet food. We see the cheap food. And then finally, when we mix it, that's the mixed food there. Here we see three more things on the other axis. We've got our units that are just the pounds of food. So for the gourmet cat food, they tell us it's 5 pounds. So there we have a 5. The cheap cat food, we don't know how many pounds of that we're going to buy, so we'll just use a variable for that. In this case, we use W. And for the mixed cat food, it's going to be the gourmet plus the cheap added together. So our units for that are just 5 plus the amount we don't know. We call that W. Now the price per unit, that part's easy. That's just the price that these things cost. So the gourmet, it says $1.75 per pound. That's where this comes from. Right here. The 50 cents is the cheap cat food. That's right here. So we just fill that in. That's how much that costs per pound. The mixed cat food, we want it to come out to $1 per pound. It tells us that right here. We want to mix the bag so that it would cost $1 per pound on average. So on the right, the final column here, our total price. The three things we see. First, this $8.75 is how much it would cost for 5 pounds of this gourmet food. So 5 times our $1.75 gets us this number here. Again, we don't know how much for the cheap cat food. We don't know how many pounds of this that we bought. So we're going to multiply some variable times 50 cents, and that's going to be the total price for the cheap cat food. Finally, for the mixed cat food, the total price, again, is going to be an expression. So it's just the price per pound, $1, times however much we buy. In this case, it's 5 plus W. So all of that goes in parentheses, and we multiply times $1. So these are the total prices that we'll see based on those things. And now once we have a table, that's how we're going to solve these problems today. Make a table, fill it out, and then use the things in your table to solve the problem, and we'll write an equation. So as you're finishing writing that down, think about what these things mean, have these numbers down, and we'll find out what is W, and we can answer our question for how much cheap cat food we need to buy. So first, we want to write and solve an equation using that information. So we know the price of gourmet plus the price of the cheaper food must equal the price of the mixed food. So what did we say the prices were? These numbers here were the prices. So we'll use those in this expression. Replace the words with what they mean. So price of gourmet, we said was $8.75 in our table, and we can check that. Plus, just addition, the price of cheaper cat food, 0.5 times W, equals, and then the price of the mixed food. Again, we're just pulling that out of the table that we already did. So, once we have all of these things written here, now we're back to solving multi-step equations, which we did much earlier in this chapter. We'll have to get W alone, so we'll just take a couple steps from that original equation. So we'll distribute everything on the right. 1 times 5, 5. 1 times W, W. So we get this. Now we want to combine our W's. We don't want that variable on both sides. We want it on one side. So we subtract that 0.5 W from both sides. On the left side, it's going to go away. And on the right, we'll get just 1/2 W. So here we see a variable plus some number equals some number. We don't need this 5 here because we want W alone. So this is just extra. We don't want that. So we'll get rid of it by subtracting 5 from both sides. So on the right, we get 0.5 W or 1/2 W. And on the left, we get, when we subtract 8.75 and 5, we get this 3.75 number. Now last thing we need to do, multiply both sides by 2. And W equals 7.5. So you could multiply by 2 or divide by 1/2. It's doing the same thing mathematically. If you divide by that 0.5, same thing, W equals 7.5. So what does that mean in the context of our problem? Well, that means that Mandisha should buy 7.5 pounds of cheaper cat food to be mixed with the 5 pounds of gourmet cat food. That would make the average price $1 per pound. Don't worry about writing all of this. Just have your variable solved for W and have that answer, 7.5, and that is pounds of the cheap cat food. First example, mixture problem done. We need to make a table, pull those things out, write an equation, and then solve it. So we can do that with just a few steps. So here's another mixture problem, but for this one, we're going to deal with some percentages. So let's just first emphasize what's important. A car's radiator should contain a solution of 50% antifreeze. Bay has 2 gallons of a 35% antifreeze. How many gallons of 100% antifreeze should he add to his solution to produce a solution of 50% antifreeze? So we want 50%. Currently there are 2 gallons of 35% in the car. We want to know how many gallons of 100% do we need to add so that the average is 50. So we're sitting at 35. We got to add some 100% antifreeze to it, and we want the mixture to come out to 50%. So how much of it do we need to add? In order to find that out, we have to make a table. So we can use G to represent the gallons of 100% that we'll add, and then we'll make a table. So here's our table. This part we need to write. Don't worry about the numbers, or don't worry about the words here. So in our table, on the left, we've got the solutions. 35, what's already in the car. 100, which we'll add. And then our final 50% is what we want. As we see our other axis, we've got the amount of the solution in gallons. And we have the amount of antifreeze. So when we multiply those things, the percentages. So first one, our amount of solution given 2 gallons of the 35 is already in the car. That says that here. So we put a 2 in this box. How much of the 100% solution do we need to add? We don't know. So that's what we need to find. That's the variable G. And for our 50% solution, we know that when we combine these two, we're mixing them. So we'll add those together. 2 plus G is what we'll get when we mix the 35 that's already in the car with the 100 that we're going to add. So we have those there. Now to get the amount of antifreeze, we're multiplying the decimal version of our percent times the amount of the gallons that we use. We turn it into a decimal because then we can get a real value out of it instead of just this. We don't want to do calculations with a percentage symbol. So 0.35 times 2, we multiply those. 100% as a decimal is just 1, so it's just 1G, or it's really just G. It doesn't change. So those two are there. For the last one, 50% is what we want. So that's 0.5. And we'll multiply times our sum for the amount of solution. So that's 2 plus g. So these amounts of antifreeze are very important. We're going to use those to solve this problem. So what do we know? Well, we know the amount of antifreeze, 35, plus the amount that we'll add, the amount of the 100, will equal our total amount that we want to come out to 50. So we just found these three things in this last column in our table. So we can say this plus this equals our 50%. So we'll write all these things and get our equation. So first, what's the amount of antifreeze in 35? Well, we said that's 0.35 times 2, and check your table, plus the amount of 100, 1G, is, what's the amount of the 50? 0.5 times that sum. So now we have our equation, and now we're back to solving. Can you solve a multi-step equation like we did 4, 5, 6 sections ago? So here we go. You start with your original, then we'll distribute that 0.5 to both things here. So we get 1 plus 1 half g equals, we simplify here, 35 times 2, 0.7, and 1g. Now we've got g on both sides of our equation. We know we want to combine those, so we can go ahead and subtract 0.5g from both sides. So notice the positive and the negative, these will cancel out. On the left, we're going to get a positive 0.5g. And now we have this 0.7 hanging over here. We want to get our g alone, so we'll go ahead and subtract that away. This will cancel out here. And we're left with 0.3 on the right. And one final step, this 0.5 and the g are tied by multiplication, so we can divide away that 0.5. And we'll solve. And how many gallons of the 100% solution will we need to add? G equals 0.6. So we'll add a little bit more than half a gallon to solve this problem. So he should add 0.6 gallons of 100% antifreeze. That will produce a 50% solution. So we started down at 35. We add some of that more concentrated 100% solution, and it gives us a 50% solution when we add exactly 0.6 gallons. Okay, so our third type of example. We're taking this information, we're breaking it down, we're writing our tables, and we're getting all these things out. For this specific problem, you need to write down the directions here. So Nita took a non-stop flight to visit her grandmother. Okay, so she's getting on a plane. That's part of the context of this problem. We're talking about air travel. So the 750-mile trip took 3 hours and 45 minutes. Okay, so that time is going to be important. All right. Because of bad weather, the return trip took 4 hours and 45 minutes. Okay. What was her average speed for the round trip? Average speed. So this is a new concept we're talking about. Average speed is going to be a little bit different than the ones we already talked about. So notice we're trying to find the speed of one vehicle. These are some of the types of problems that you'll do today. So we'll have to use this context to help us solve it. Well, what do we know? We know that Nita did not travel the same amount of time on each portion of her trip. The first one was faster, the second one was slower. So we'll need to find the weighted average of the plane's speed. We're asked to find the average speed for both portions of the trip, which we can do that. So first, we'll have to find the rate of the going portion. So when she leaves, we call that the going portion. And then find the return portion. So when she's on her way back, find the speed there as well. Because the rate for this one, we're going to keep it in miles per hour. We need to write our hours and minutes in a decimal form, because then we can calculate what's going on there. 3 hours and 45 minutes isn't all together in one number that we can easily do multiplication with. So 3 hours and 45 minutes, we'll convert that to a decimal. 45 minutes is 3/4 of an hour, so that's 0.75. So we get these decimals here, 3.75 and 4.75. We will use those in our calculations. So going, when she's leaving, what do we know? This rate is in your book for this section. It's going to be used in some problems. So we know that our rate is going to be distance over time. So what distance did they travel over how long it took will give us that rate. In this case, it's going to be miles. Miles for distance, hours for time. So we'll use that. So first, 750 miles when she left. That's how far she covered. How long did it take? The time, 3.75 hours. Divide that away, you get 200 miles per hour. We'll do the same thing for the return flight. So same distance, but it took a lot longer. So we divide that away, we get about 158 miles per hour. Very important. It makes sense now that the miles per hour is lower on the return flight because it took longer. They were flying slower. So that's our rate. Miles divided by hours, miles per hour. So we have that rate there. So because we're looking for a weighted average, we can't just average the speeds. We need to find the weighted average for the round trip that takes into account the timing of how long it took. So first, this looks like a whole lot of stuff to digest. Don't worry about writing this down. There is more information in your book if you want to check it out. But we're going to fill these things in. So what do we know is happening in this formula? The rate of going is the miles per hour. So what is her speed when she was leaving? And then how long did that take? Plus, what was her rate when she returned? Times how long did that take? We'll divide all of that by the time that it spent for her to leave and the time spent returning, summed together. We're finding the overall average weighted for her speed, and this will give us that overall weighted average for everything for the whole trip back and forth. So we plug all those things in. We said her first rate when she left was 200. She flew for 3.75 hours. Plus, her rate on the return was 158. Times she flew for a little under 5 hours. We divide all of that by the sum of how long the travel was. So 8.5 hours when you add those together. And now all we have to do is simplify. So you can do this by hand or plug into a calculator, and we'll get that final solution. So when you multiply all that out and divide, we see our average rate was 176, and we'll call that miles per hour. So this is her average speed for that entire trip, about 176 miles per hour. We found that with that weighted formula. So this formula is in your book, so that can be used to help you solve any of the example 3 type problems in this section. Okay, last one for today. So let's not worry about writing the words for this one. You just need to make sure you get the table. So in this case, we're talking about the speed of multiple vehicles. So first, let's read the problem and circle what is important. A railroad switching operator discovered that 2 trains are heading toward each other on the same track. So we've got 2 trains. They're heading towards each other in opposite directions. Currently, the trains are 53 miles apart. So that's the distance between them. One is traveling at 75 miles per hour, the other at 40. The faster train will require 5 miles to stop safely, and the slower one only needs 3 miles to stop safely. So about how many minutes does the operator have to warn the train engineers to stop their trains? So very interesting problem. This is the type of engineering that has to take place for emergency situations like 2 trains going towards each other on a track. So we'll use these numbers, apply them, and then understand how many minutes it might take to warn the engineers to stop the trains. So first we'll need to use those numbers, and we can draw a diagram to help us understand what's happening. So we already said they're 53 miles apart, so we can imagine that's the distance here. This one's going to take 5 miles to stop. This one will take 3. So we know that, we have that, we're good to go. And we can now talk about our table that we need to fill out. Before we do that, quickly we can calculate. The total miles is 53. If you subtract the 5 and the 3 that they need to stop, we really only have 45 miles of distance, safe distance between those two trains, because 8 of those miles aren't safely available for the trains because that has to be used for them to stop. So we have 45 miles of free space there. So if we let M be the number of hours that the operator has to warn the train engineers to stop their train safely, we can make a table. So the fast train, what is the rate? We have the fast and the slower one, fast and slow. Here we have our rate in miles per hour, the time, so how long they can warn them, and our total distance, which will just be our rate times time. And we talked about that already. So distance is always rate times time. So we'll multiply 75 for the fast train, miles per hour, times however long they have to warn them, we don't know, is going to equal 75 m. That's going to be the distance. The other train, 40 times m, 40 m. So we should have that table, and we can now understand what's happening there. So third step, now we need to take that information and make some kind of an equation, use that information, and solve the problem. So the distance traveled by the fast train, we said is 75 m, plus the distance traveled by the other train, 40 m, is 45 miles. So 75 m plus 40 m must be 45. That's how long they have distance-wise between the two trains. So there's our original equation. We add those together. We'll divide away that 115, and we know how to do this. We've done it many times. We get m to be about, if we round, 0.39. And remember, the units we said for m were hours. So m is 0.39 hours. That's not that useful for us to know. We want to know if it's less than 1 hour, okay, how many minutes is that? So if we want to convert this hours to minutes, what do? Well, we multiply it times 60. So we convert 0.39 times 60. How many minutes does the operator have to warn? 23.4 minutes. So there we see that. So they have a little more than 20 minutes to warn the operators that they're going in the wrong direction before those trains would crash. So there's our solution there. And now we can move forward. So there's a lot of writing in this section, a lot of things we have to remember. If you write down your tables, it won't be too bad. So have your tables, write down the things from the word problems, make an equation, and then solve it. If you break it down, you can definitely do these problems. There's nothing much to it.